this is the product, the food product. Okay. So as you know, this is small q is the rate of heat transfer or heat transfer rate. So U1 is the overall heat transfer coefficient in evaporator 1. A1 is the heat transfer area in evaporator 1. Okay. Delta T1 is the temperature difference in evaporator 1, which is Ts minus T1. Okay. So in the second evaporator, similarly, remember that the steam in the second evaporator is the vapor from the first evaporator, and that this will condense at approximately the same temperature as it boils, since pressure changes are small. So Q2 equals to U2 A2 delta T2. Okay. So subscript 2 indicate the condition in second evaporator. So if the evaporators are working in balance, then all the vapors from the first effect are condensing, and in their turn, evaporating vapors in the second effect. Okay. Also, assuming that heat losses can be neglected, then there is no appreciable boiling point elevation of the more concentrated solution, we assume. Okay. So, and the feed is supplied at its boiling point. Okay, I think got some people waiting, is it? No. Let me see. Okay, no. All right, sorry. We will continue. Okay, so we're assuming there's no heat losses and there's no boiling point elevations. So we can write these equations. Q1 equals to Q2. All right. So further, if the evaporators are so constructed that A1 equals to A2, this is the area, the foregoing equations can be combined. So U1, A1, delta T1 equals to U2, A2, delta T2. So, and then A1 and A2 is the same, you can cancel out, become this, U1 delta T1 equals to U2 delta T2. And then you can see delta T1 over delta T2 is inversely to U2 over U1. So state that the temperature, equation 8.2 mentioned that the temperature differences are inversely proportional to the overall heat transfer coefficient in the two effects. Okay, this is the overall heat transfer coefficient for effects 2. This is for effect 1, but they are opposite. Okay, so now we go to feeding of multiple effects evaporator. Stop sharing. All right. So the feeding of multiple effect evaporator in two effect evaporators, the temperature in the steam chest is higher in the first than in the second effect. Okay. In order that the steam provided by the evaporations in the first effect will boil off liquid in the second effect, the boiling temperature in the second effect must be lower. So the boiling point of the food, of the feed, right, must be lower. So consequently, the pressure in the second effect must be reduced. Okay, you must reduce the pressure below that in the first. So when the pressure is reduced, the boiling point of the liquid will be reduced, easier to be evaporated. So in some cases, the first effect may be at a pressure above atmospheric, or the first effect may be at atmospheric pressure, and the second and the subsequent effects have therefore to be under increasingly lower pressure. It must be lower and lower, so the pressure is lower, the boiling point will be lower. Okay. So often many of the latter effects are under vacuum. The last part is under vacuum. So under these conditions, the liquid feed progress is simplest. So the feed also got easier because from high pressure to low pressure. Okay, it passes from effect 1 to effect 2 to effect 3 and so on. As in these circumstances, the feed will flow without pumping. So you don't need to pump because the pressure will be lower and lower. So first effect is higher pressure, so they will go to second effect, which is lower pressure. So easier for the liquid feed to go through. No need to introduce any pump to direct the flow of the feed. Okay, so this is called forward feed. It means that the most concentrated liquid will occur at the last effect, the one like at vacuum usually, last one. So easier for evaporations. Okay. Alternatively, feed may pass in the reverse direction, starting in the last effect and proceeding to the first. But in this case, the feed or the liquid has to be pumped from one effect to the next against the pressure drops. All right. So this is called backward feed. And because the concentrated viscous liquid can be handled at the highest temperature in the first effect, it usually offers larger evaporation capacity than forward feed system, but it also may be disadvantageous from the viewpoint of product quality because of very high temperature. Okay, denaturations due to high heat. So advantages of multiple effect evaporator. The optimum design of an evaporation plant must be based on the balance between operating costs, okay, which are lower for multiple effects because of their reduced steam consumptions. You use lesser steam, right? Okay, because you recycle the vapor. Okay, and capital charges, which will be lower for fewer evaporators. Okay, if you buy more evaporators, you will have more capital costs. You know, in industry, right? You have operating costs, that the daily one, and then this is the machine cost, the capital cost, right? Okay, so the comparative operating costs are illustrated by in table 8.1. So if the capital costs were available, they will decrease the advantages of the multiple effects. All right. So here we do not consider the capital cost. We just want to compare the operating costs, just the running costs. All right. So you can see number of effects, just one evaporator. Steam consumptions. So you need 1.1 kg of steam in order to remove 1 kg of water from your feed. Okay. Total running cost. Okay, relative to a single effect evaporator, 1.1 divided by 1.1 equals to 1, right? So relative, this one is compared with 1, okay? Of course, it's 1. When you have two effects, okay, it's found out that you only need 0.57 kg of steam in order to remove 1 kg of water. So 1 kg of water evaporated means you use lesser steam here. So you save a lot of operating costs. So its total running cost is 0.52. If you have 3 effects, it's 0.4 kg of steam needed to remove 1 kg of water. So you save more. The total running cost is even lower. It's 0.37. All right. So now we studied vapor decompressions. So vapor compressions means raising the pressure of gas by reducing its volume. You compress the gas, so it will increase the pressure by reducing the volume. In addition to the possibility of taking the steam from one effect and using it in the steam chest of the other, a further possibility for economy of steam is to take the vapor and after compressing it, return it to the steam chest of the evaporator from which it was evaporated. So you are not going to evaporator, the vapor from evaporator 1 is going back as the steam for evaporator 1, not going to evaporator 2. Okay, going back to the original one. So the compressions can be effected either by using some fresh steam at a suitable high pressure in a jet ejector pump or by mechanical compressor. So you can compress them, increase the pressure back. Okay, by this means proportions of the vapor are reused together with fresh steam, and so considerable overall steam economy is achieved by reusing the latent heat of vapors over again. So the steam economy of the evaporator is also affected by the temperature of the feed. So if the feed is not at its boiling point, heat has to be used in raising it to this temperature. So a convenient source of this feed preheat may be in the vapors from a single effect evaporators. So a separate feed preheater can be used for this purpose. So you heat the feed, okay, let's say the milk, okay, so to its boiling point, so you can save a lot of steam economy as well, because the heat no need to be used for the sensible heat. Okay, as evaporation proceeds, the liquor remaining in the, okay, now it's about boiling point elaboration. Okay, as evaporation proceeds, the liquor remaining in the evaporator becomes more concentrated and its boiling point will rise, as I told you before. So when you add some unvolatile, non-volatile solute into the solutions, that will increase the boiling point of the solution, like the salt, right? Salt water have higher boiling point than pure water. So extent of the boiling point elevations depends upon the nature of the material being evaporated and upon the concentration changes that are produced. Extent of the rise can be predicted by Raoult law. So I'm sure you haven't learned this before, Raoult law. So where delta T equals to Kx, where delta T is the boiling point elevations, X is the mole fractions of the solute, and K is a constant of proportionality. So it's the molar boiling point elevations constant. Okay. In multiple effect evaporators, where the effects are fed in series, the boiling point will rise from one effect to the next as the concentrations rise. Okay. Relatively, less of the apparent temperature drops are available for heat transfer, although boiling points are higher, as the condensing temperature of the vapor in the steam test of the next effect is still that of the pure vapor. So, as the concentration rises, the viscosity of the liquor also rises. The feed also will become more viscous. So the increase in the viscosity of the liquor affects the heat transfer, and it often imposes a limit on the extent of evaporations that is practicable. So there is no straightforward method of calculating or predicting the extent of boiling point elevations in the concentrated solutions that are met in some evaporator in the practical situations. However, we can use these daring rules. So this is something new too, I believe. So the rings rule state that the ratio of the temperatures at which two solutions, okay, usually the one reference solutions will be pure water, okay, exerts the same vapor pressure is constant. Hence, when we take the vapor pressure temperature relations of a reference liquid, and if we know 2 points on the vapor pressure temperature curve of the solution, we just need 2 points, okay? That is being evaporated. The boiling points of the solutions to be evaporated at various pressures can be read off from the diagram called a daring plot. Okay, so later we will do an exercise so you will understand more about this daring rules. Okay, all right. So daring plot will give the boiling point of solutions of various concentrations by interpolations. So at various pressure and at various pressure by proceeding along a line of constant compositions. So I will show you the figure so you will understand what it means by this sentence. Okay. So a Daring plot of the boiling points of sodium chloride solutions is given in the next slide, figure 8.3. Okay. So reference, this is the Daring plot. So it's like about two boiling point of two solutions. One is the boiling point of solutions that you want to know. Another one is the reference solution, is usually the pure water, right? So for example, okay, for boiling point of water at atmospheric pressure, right? We know it's 100 degrees Celsius, okay? So 100 degrees Celsius, you go up, okay? So for, let's say this is the sodium chloride solutions at 0%, means there's no sodium chloride, sodium chloride at all. So it will also be 100 degrees Celsius, the boiling point. Okay, but when you increase the solute, you add more sodium chloride, let's say 5%, then 10%, 20%, 25%, and then the last one, saturated maximum. Okay, saturated. So when you go to 100 degrees Celsius for water, it will be 110. Okay, 110 for the saturated sodium chloride solutions boiling point at the same atmospheric pressure. Remember, here at 101 kilopascal, water boil at 100, right? So let's say water boil at 70 at, let's say, 63 kilopascal, right? Okay, water will boil, boiling point of water will be lower at lower pressure. So when you read this, you must think, synthesis new informations. So this also indicate that this is various pressure. Okay, the boiling point of water at various pressure. Because at atmospheric pressure, boiling point is 100 for pure water. Okay, so 110 means here is higher than atmospheric pressure. So 110 for pure water. Okay, so it's higher pressure. Okay, when you have lower pressure, lower boiling point. Higher pressure, higher boiling point. Okay, so this is mean water. All right. So also one thing we can we can read from this. Okay, 10 minutes warning. Okay, so one thing we can read from this chart is that at various pressure, okay, all the saturated, okay, or the different concentrations of sodium chloride solutions, their boiling point are higher. Okay, you see the line is all on top of the line of the pure water, 0, right? 0. Okay, so by finding the boiling points of salt solutions of various concentrations under two pressures, the Darling line can then also be filled in for solutions of these concentrations. Okay, such lines are also on figure 8.3. Okay, so like intermediate concentrations can be estimated by interpolations and so the complete range of boiling point at any desired concentration and also under any given pressure can be determined. Here is the any desired concentrations. Okay, you can interpolations. Okay, 5, let's say 7.5, you get the middle line. Okay, all right. So and then at any pressure, because here is boiling point means it's also a different pressure. At atmospheric is 100. Lower than atmospheric 90 degrees Celsius, water will boil. Okay, so latent heats of vaporization also increase as pressure are reduced. as shown for water in table 7.1. Okay, as you see, when the pressure is reduced, the latent heat of vaporization will increase. But when the pressure will reduce, the boiling point will reduce. Pressure increase, boiling point of the liquid will increase. All right. Okay. Just here, 1 atmosphere, 101 kilopascal. Okay. For water, is 100 degrees Celsius. So when you have like lower, okay, like 20 kilopascal, you have 60 degrees Celsius of boiling point for water. But latent heat is opposite. Just as I told you before in the appendix 8, the opposite relationship. So when this pressure is decreased, latent heat will be increased. So now we'll do a last exercise, I guess. All right. So you will understand more. So try to, if you have graph paper, so try to draw this on a graph paper. If you don't, then just draw with a scale on a blank A4 paper on scale. All right. So you still have 6 minutes. All right. Okay. So just draw in the blank paper. Okay. According to the scale of your, you draw the scale by your, according to your ruler.